So let's talk about program critical timeline and program implementation. Let me say that at the very end of this professional development, we're going to go over the navigation of the website. But as part of these chapters, I may jump in to the website to show you some things. So I'm going to go ahead and share my screen right now. And are you able to see the website? Okay. So you'll see lots of navigation buttons on the top. Again, we're going to go into the details. But under teacher resources, there's a bunch of web pages. Under flight opportunities, there's a bunch of web pages. Let's concentrate on the flight opportunities main button. And you'll notice that if I scroll down to mission 21, which is your mission, you'll see three subpages show up on the side: critical timeline, mini lab operation, and mission patch art and design competition. I'm going to go to that first subpage, critical timeline. And what you'll see here is a bulleted list of all of the deadlines and milestones associated with this program. The first section, by the way, is titled Experiment Design Phase, the timeline through selection of flight experiments. And the second section is titled Flight Operations Phase, the timeline through return to Earth of flight experiments. So this provides you an understanding at granular level of all the milestone dates and the deadlines associated with this program. I wanted to show you this to say it's all on the website. In fact, everything I'm talking about today is on the website. So now I'm unsharing my screen, and let me tell you about the top level milestone dates. So program operations officially start on September 2nd, though if a community wants to start a little bit earlier to get an advanced jump on program, we can hold the professional development early like we're doing now, which is about 2 weeks before program start. What does it mean that the program officially starts on September 2nd? It starts a 9-week clock. And over those 9 weeks, you're delivering the microgravity curriculum to your students. The students are breaking up into teams. They're designing their science experiments, and they're writing their formal proposals, making the case for why they ought to get your flight slot. So by the beginning of November, after that 9-week period, proposals are due to you. Then your step 1 review board does its thing and selects 3 finalist proposals, sends them to us. Our step 2 national review board selects your flight experiment, and that is done by December 19th. So you can put out a big press release just before the holidays. Your flight team will then have 2 months to optimize their experiment. And at that point, the fluids and solids, what we call the experiment samples, have to be locked in, and that list goes to the toxicology office at Johnson Space Center for 4 months of flight safety review, which means the earliest the launch can take place is early June of 2026, and the launch could certainly be delayed. So does everybody understand how that timeline works? Does that all make sense? Now, with regard to implementation, at the pre-college level, undergraduate institutions do implementation a bit differently. But at the pre-college level, Pam, I'm assuming that your teachers that are participating in this are saying, I'm going to do this with my entire class. Is that correct?
At the elementary and middle school level, yes. At the high school level, we're doing it in a variety of ways. We're doing some class, some independent design, so independent choice. So we're doing a combination.
So in that case, at the high school level, you're expecting the students to be more self-directed learners.
Yes.
Because otherwise, a teacher, I don't know how a teacher is going to deliver the curriculum to 1 or 2 students at a time. So there, the students
we also are doing special sessions. So once I hear all of this, we'll be able to plan appropriately.
So you might say, you might put out an invitation across the high school and say, if you're interested in doing this, come to a special session where we're going to train you on the curriculum. Great model. So that works very well. So Let me explain, drill down a little bit in terms of what Pam said. So you have a minimum student engagement of 100 students because we want a big enough proposal pool to pass flight safety review. Your implementation plan is targeting, I think, at least 300 students to participate in this program. So you can't do this by saying to your class, who wants to do this? And you've got 2 students saying, we want to do it, because I don't know how you're going to deliver the microgravity curriculum just to 2 students. The way it's done is that a teacher says, I'm going to do it with my entire class, delivers the curriculum to the entire class as in class time, and then breaks the students into formal research teams of typically 3 to 5 students per team. So if you have 30 students in your class, you're going to have 6 to 10 teams, and you're designated the teacher facilitator. Now those student teams are in a real research proposal competition, and so they can't talk to each other. The teams are not sharing any information. In the real world, if professional teams did that, it would be a firing offense. And so typically at the pre-college level, once the students are now designing their experiments or writing their proposals, they're doing that as out of class time. And depending on how it's structured at PV schools, it could be in the library, at lunchtime, in cubbies, after school, independent study, homeroom. But the point is that typically it's done at the pre-college level as a mixture of in-class versus out-of-class time, where the curriculum is delivered in class and the experiment design and proposal writing is delivered as out-of-class time. So does anybody have any questions, comments about that? Pam, you might want to jump in to provide some guidance to your team here, but that's typically the way it's done from the vantage point of the national program. I guess no questions or comments, all sounds good? Okay, so now let's go on to another aspect of implementation, and this is really up to you all to figure out how you want to do that. But let me give you a sense of real STEM. In the real world, there is no such thing as STEM. There is no distinction between science, technology, engineering, and math. It's all one seamless landscape with no disciplinary boundaries whatsoever. And a researcher, when they dare to ask a question, and they need to, which defines a problem to be solved, they need to move across this interdisciplinary landscape at will to secure the core knowledge necessary to solve the problem. The reason we have an acronym called STEM is due to how we've compartmentalized disciplines in formal education. If you want to go to learn math, you typically go to a thing called a math class. And math is the language of nature. If you want to understand how nature operates, you need to speak her language. But we often teach math in isolation from nature, and we wonder why students are coming out of math class generation after generation, asking the question, why do we even have to learn this stuff? And the best answer that we have is, well, you never know when you're going to need trigonometry. That is not the way the real world works. It's antithetical to the way the real world works. In the real world, by definition, it is interdisciplinary. And if you're going to bring a real world interdisciplinary experience into the classroom as a project-based learning approach, you would like to see an interdisciplinary team of teachers involved to reflect that authenticity. What does that mean? Well, as I said before, the engineering and technology constraints put guardrails on the science experiment that can be done. So you can imagine a science teacher delivering the science curriculum portion of on microgravity. You could foresee engineering and/or technology teachers delivering the Minilab operations manual, the Minilab operations page with all the engineering and technology constraints. The students are going to write real research proposals, grade level, against a proposal guide, technical writing skills with embedded citations and a bibliography of primary references. So you can imagine reading and literacy teachers getting involved. And you can also imagine that art and design and history teachers are involved for the Mission Patch Art and Design competition. Do we have communities where it's only the science teacher doing that? Sure. Do we have communities where they're trying to do this in an interdisciplinary way? Sure. Do we have communities where there are designated STEM teachers whose job it is to provide that interdisciplinary connection, set of interdisciplinary connections? Sure. It's really up to you to figure out how you want to do it. But I'm just giving you a sense of the real world and how you have the ability to kind of mirror the real world with interdisciplinary teams. Anybody have any questions about that? Comments? Everybody good with what I just said? Okay, cool. So now let's talk about something else. Your students, your student teams, you're a teacher facilitator for a bunch of teams, and your teams are going to come up with lots of ideas for science experiments. They're going to be coming from various different disciplines, and you know what? They're going to have questions. And the initial sense of this is that when they have questions, you know who they're going to come to. They're going to come to you. And you are not going to be an expert in any of the disciplines associated with those experiments, which can cause enormous amounts of stress and anxiety. We have a solution. And if you order right now, we'll send you an extra set of steak knives free. Okay? Here's the deal. As soon as a student team understands the discipline focus of their experiment, they need to get a researcher advisor who is an expert in that discipline, so that that researcher advisor is the go-to person for their questions. Everybody understand where I'm coming from on this? And I will show you on the website where it is that we talk about how each team can get a researcher advisor, but let me kind of walk you through the process. Each team uses Google Scholars Search. And if you've never done Google Scholar Search before, it's a way cool search engine. What you're going to do is put in the keywords that represent that experiment. So let's say a team says, I want to do planaria worm regeneration on the International Space Station. That's a really cool idea. They need to get a planaria worm regeneration expert. So they go to Google Scholar Search, the link is on the website, and they put planaria worm regeneration in the search box. And when they hit return, what will be returned are scholarly peer-reviewed research papers on planaria worm regeneration, representing the state-of-the-art human understanding in that discipline. We are not asking your students to read the paper, but to go to the top of page 1 where the authors are listed and their host institutions. And if Dr. Jane Smith is a co-author on a planaria worm regeneration paper, she's an expert. And if she's at Harvard, your student team goes to the Harvard website, goes to the staff directory, gets Dr. Jane Smith's email address, and sends a really nicely worded email to Dr. Smith asking if Dr. Smith can be their researcher advisor. And if the student team sends 20 of these emails out to possible researcher advisors, all they need is one to say yes. And on the website, we have a template for a really nicely written email that each team can customize to their experiment to secure a researcher advisor. So does everybody understand that approach to things? Okay, that should kind of make you feel good. All right, so that is how, that's an overview of the timeline and how this is typically implemented as a combination of in-class versus out-of-class time, how it can be implemented by an interdisciplinary team of teachers, and how it's important for each team to get a researcher advisor to take the burden off of you from those teams. And the other piece I need to tell you is we have a flight operations team that is available for questions at any time. And if you have questions or your students have questions about experiment design or proposal writing, we tell them submit the question via the contact button because we need the question in writing. And as soon as the question comes in, it goes to the entire flight operations team, And that team will know where to route the question. It might be a question we have to route to NASA toxicology, for instance. That's why we need it in writing. But the reason I say this is we have your back. We have a national team over here that can answer questions that come in from students and teachers. So we want to make you understand that this program is well thought out. We understand the issues on your side of the fence, and we want to take that into account when we design this program. Any questions about implementation or timeline? Okay, so I'm going to do it again. I'm going to stop the recording. And before I start, okay, wait.